Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look at adding new functions to the existing array library. Today we're going to be adding two new functions to our array functions library. As a developer, you will probably be using a great number of arrays within your applications, as they're a good way to store information in memory while you process it. However, there comes a time when you have to both save and load these arrays to disk. As you will see on screen, we have included this library as an include file. This include file has three constants that need to be set up before the file is included: index search, index start, and indexed end. These constants are required within the library and only need populated if you're going to be doing indexed searches on arrays. So for the moment, we're setting them to false, 0 and 0. As we're going to be working on an array, our first task is to declare the array. So within the pb main function, we're going to declare but not size our array. So we will use the dim command to specify an array, in this case an array called data. We have the prefix of a for array and str for string, to indicate that this data array is going to contain string information. We have not yet specified how many rows or columns that exist within this array. So we will create a small function whose job it will be to populate and dimension the array. PowerBasic will allow you to create an array with up to 8 dimensions. You will probably use one-dimensional arrays a great deal within your applications. You will occasionally use two-dimensional arrays and possibly rarely three-dimensional arrays. I've only on a couple of occasions ever needed to have a four-dimensional array. But the functions we're going to create today will handle up to the full 8 dimensions. So let's create this first populate one-dimensional array function. So we're going to call this populate 1D array. So here is our populate 1D array, taking a single parameter, which is basically a pointer to our data array. As we're passing this by ref, it's only passing a pointer to where the array data exists in memory. You're not actually passing all of the data within the array. So the name we have in this parameters list does not necessarily have to match with the name in the calling function. But it does have to be the same type of data, in this case string. So within this function, we're doing a redim command to redimension the data array for 100 elements as string. Writing the redim command like this is exactly the same as writing it as 0 to 100, as if you miss this first bit out, it automatically assumes that you wish to have a 0 element in the array. We're following this with an array assign command. This allows you to populate your array with data. For a one-dimensional array, this is very straightforward to see and understand on screen. Following the array assign, we have the name of the array, two brackets, an equals, and then a number of values. In this case, we're populating the 0 element of the array, which is the first element with the word header, and then the first 6 letters of the alphabet falling into each subsequent record in the array. So now that we've populated this one-dimensional array, we'll need a way of actually printing this out to screen. So we're going to create a print 1D array function. Again, this is taking a single parameter, which is our by reference pointer to the data array. Again, this is working on a for next loop. We know in this case there only are 6 elements populated within the array, the 0 to the 5th element, and we're building up those values into a data string, adding on each element as we go with a space between them. We're then adding on the words with and the number of rows using the ubound command. And we're using the fun.log command to print the data out so the user can see it. So if we go back to our pb main function, and we will slot in the call to our print 1D array function. So let's try running the application for the first time. So our application has now run and displayed on screen the contents of our one-dimensional array, printing out the first 6 elements and telling us it's got 100 rows in the one-dimensional array. So our task now is to create the first of our 2 New Functions. We want to take the array we have prepared and we want to save this out to disk. So first of all, we will create a local variable called location, and we will populate that with the exe path and the name of the file we wish to create. In this case, teststring array. This will be a straightforward text file. And we've also dimensioned another local variable called error. Should there be any error in actually saving to this file, the error details will be populated into this error variable. So we're going to create a new function in our library called binary save the string array data with header. This new function will take three parameters. First of all, the name of the array we wish to process, secondly, the location into which we wish to save it, and finally, an error variable, which will be populated should there be an issue saving to the file. If this function returns true, then we know the string array has been saved successfully. If it returns false, we can print unable to save the string array. And we can tack on to the end of this message the error should one have occurred. So let's now go into our library and start to create this new function. So we've now loaded up our include file. And we've created the skeleton for our new function binary save the string array data with header, passing the three parameters: the name of the array, the location we're going to be saving to, and an output variable which will be our error should one occur. Since this function is going to be called regardless of how many dimensions the array actually has and regardless of the size of the array, we need to do some working out within this function to see how many dimensions we're talking about. Because when it comes time to load this file back up into memory, into an array, we'll need to know how many dimensions are going to need to be populated. So we're going to create four local variables. The file variable is a handle for the file we're going to create. The string header is going to be used for the number of rows in each dimension in the array. This header variable is going to be written to the first part of the file. The next variable is a long variable which will be the dimension counter, as we're going to step through each of the dimensions from 1 to 8. The final variable is the range. This will be the number of elements per dimension. So we're going to create this header with a 5-character limit. This will be the number of rows in each of the dimensions. If you're likely to create arrays with more than 99,999 rows, you can always make this a 6-character limit to make it larger. So our first task is to work out just how many dimensions does this array actually have. We can do this quite easily using the ubound command within a for next loop. We're stepping through the dimensions from dimension 1 to dimension 8, and we're populating the range variable using the ubound command. The ubound command has an option for the dimension number. We need to give it the name of the array, in this case str array, and our second parameter is the dimension number. So the first iteration of this loop will be for dimension number 1. We have created an array that only has one dimension, so this will give us the number of elements, the upper bounding of the array. In this case, this should return the value of 100. If the array does not have that particular dimension, for example dimension 2, the range value will be 0. So we're building up our header variable with each of these values, and we're delimiting them with the pipe character. And we're right-filling them into a 5-character string. So this will be 0-filled. And at the end, we're doing a right-hand trim to trim off the last pipe character. So having prepared our header with the number of rows for each dimension, our next task is to ensure we wipe the file should it exist at the current location. We can do this quite easily by checking using the isFile command. This will return true if the file currently exists, and if it does, we can use the kill command to delete it. Now we're ready to actually start saving our data to the file. So we're going to do this in a try-catch block to catch any errors. So we're using the free file command to pick up the file handle, and then using the open command for the specified location for binary access write, using the file handle we have just obtained. This will open a file all ready for writing. We can then use the put command to put the header variable out to that file. Having put our header out to the file, we now have to put the contents of our array, We can do that with a single line of code. The put command takes 3 parameters: the file handle, the character in the file you wish to start at, so our header starts at the first character, and our array, we're using the length of file for the file currently. So however big the header is, this is going to add on to the end of the file, and we're going to specify the array we wish to write to the file. So this will dump a binary image of our array into the file. We can then complete our try-catch block by catching any errors in the catch statement. And in the finally section, we're closing the file. So this function will return true if the saving to the file was successful, and it will return false if it was not. So now that we've completed the saving routine, let's try running the application to see if we can create a file. Well, it's telling us the string array has been successfully saved. So let's have a look on disk to see how it appears. And there at the top of our folder is the test string array.txt file. If we open that up, we will see there are our 8 dimensional records. We have 100 in the first dimension and 0 in all of the others. And following that, we have the data coming from our array, the word header and the letters A, B, C, D, E and F. The rest of our array is unpopulated, therefore it's appearing as blank. But it would appear we have successfully managed to save our file to disk. Our next task is to create a routine to load this back into memory. So before we do that, we're going to wipe the contents of the array. We can do that quite easily by using the reset command. This will change all of the values within our data array back to empty length strings. And to prove that has actually worked, we can call our existing function to print the one-dimensional array. And then to prove to ourselves that this has indeed changed our array, we're going to redimension the array with fewer records. So if we run our application now, it will save the string array, wipe the array, tell us that the array has no data, but still has 100 rows. We have now recreated the array with only 10 rows. So at this point in the application, the array does exist, but it has only 10 rows in it. So our next task is to create our second function, the one which is going to load our string array back into memory. So we're going to call this function binary load the string array data with header. And as we did in the previous function, if this returns true, then the data has been loaded. If it returns false, then we will say it has been unable to load the string array. And having loaded successfully the string array, we will then print the data back out to the screen to ensure our data has come in quite correctly. So let's now go into our library and create this new function. So here is the skeleton of our new function taking its 3 parameters: the reference of the array to load, the location to load from, and an error variable should we encounter any errors. At this point in the code, this function has no idea how big the array is or how many dimensions it has. So it's going to have to read the header at the beginning of the file to work that data out. So we're going to have to create a number of local variables to allow us to process this. So as before, we have a file handle variable. We also have a variable for the number of records which have been returned. And we have a string variable which is going to contain our header information. Then we have the number of dimensions in the array and a dimensional loop variable. And we're creating a small single-dimensional array to hold the range for each dimension. This is the number of elements that each of the 8 dimensions could have. So first of all, we will populate the header variable with 47 spaces. We're using the value 47 because this is the length of the header in the file, containing the information on each of our dimensions. So again, as we did before, we need to use a try-catch block to trap any errors when we're opening the file. So again, we're using the open command and the location of the file. This time for binary access read, as the file handle we have just created. This time we're going to be using the get command. It takes 3 parameters: the file handle, the character position to begin at, in this case the first character in the file, and we're populating the header variable. As the header variable is currently 47 spaces in size, it will read the first 47 records and populate the header. Now that we have the header variable populated, we can use a for next loop to populate our long ranges array. This will have the maximum value of each of the elements in each of the dimensions. As you will remember from the file, if the value comes back as 0 for the range, then that dimension is not in use. So as we're currently handling a one-dimensional file, only the very first record will actually have a value, in this case 100. So now that we've got to the point of populating this array, and we know how many dimensions we have because we've been counting them up, using this variable, which has been incremented every time we find a range greater than 0, we now have to redimension our array for the number of dimensions we have. We can do this quite easily using a select case command. As we know, in this particular case, we have only a one-dimensional array. Therefore, we want to use a redim command going for that number of records. So the value held in this array will be 100. So we will dimension our array as 100 elements. And having done that for a one-dimensional array, we just have to do exactly the same for each other dimension. So we will have a case statement for 2-dimensional, 3, 4, all the way up to 8-dimensional. And for the 8-dimensional array, we have 8 parameters for each range in each dimension. And should there be a number of dimensions other than 1 to 8, it's either going to be 0 dimensions or greater than 8. So in this case, it would look as though the file has been corrupted. So we will return false and put an error message in to say it's either 0 or greater than 8 dimensions. And we will exit the function at that point. So now that we've dimensioned the array, we now can get the data beyond the header in the file. And as we did before, we're using the get command with its 3 parameters: the file handle, the position within the file we wish to start at, in this case the length of the header plus 1, and the final parameter is the array we wish to populate. And it will also populate a records variable. This is the number of records put into our array. And at that point, we can return true to the calling function. And as we did before in our try-catch block, we can handle any errors in the catch statement, and in the finally part, we can close the file off. So now that we've created the second function, we should be able to read this data back into memory. So if we go back to the PB main function, we can see after the successful running of binary load to string array data with header, we will print the one-dimensional array out to our screen, and the application will then terminate. So let's try running the application to see if we actually get our data back out again. So at the top of our screen is our original population of the one-dimensional array with 100 rows of data. We successfully save that to disk. We then wipe the array so there is no information left in the array but still 100 rows. We then redimension the array to give it only 10 rows. So at this point, we can then attempt to reload the array. So the array has been reloaded with the same information we had originally, and it is now back up to 100 rows. So we have successfully created a one-dimensional array, saved it to disk with a header, and reloaded it. So will our functions work effectively for 2- and 3-dimensional arrays? Let's go back to the code. So we had a function called populate1darray. We will comment this out, and we will create a new function to populate a 2-dimensional array. The location is still going to be the same place, and we also want to create another function to print out this 2-dimensional array. And we will comment out the 1-dimensional one. So we've now replaced all the calls to the print1d array with a call to a print2d array. So here is the function to populate a new 2-dimensional array. We're going for an array for 100 records and 5 columns. And we're populating again header, and we're going for uppercase ABC and lowercase abc. Into the 0 element for the header, the first row for the first 3 characters, and the second row for the next. So we also need something to print this 2-dimensional array out to screen to prove it's been successfully saved or loaded. So again, a very similar function to what we've done for the one-dimensional array. It's a for next loop, printing out the first 2 rows and the 3 columns, and printing out the number of rows in the first dimension. So we now try running our application once more for this 2-dimensional array. So we can see our array has been created with its data with 100 rows. We have successfully saved the string array to disk. We have wiped the array, giving it no data, but with 100 rows. We have redimensioned it to have 10 rows. We have loaded the array back up from disk with the same information, and our application has successfully handled a 2-dimensional array. So let's just have a quick look at this 2-dimensional array. And we will see there are our headers. Our first dimension is 100, our second dimension is 5, and the remaining dimensions are all 0. And there we have the header and the data scattered through the rest of the file. So let's finally add a third dimension. So as we did before, we need to add a function to populate a 3-dimensional array. And we will need a function to print out that 3D array. And we will replace the calls for printing 2-dimension with 3. So here is the function to populate our 3-dimensional array. We have dimensioned now 3 dimensions, 100 rows, 5 columns, and 2 elements in the third dimension. And we've populated each of these, again with a different combination of letters. So as we did before, we will create another function to print out the 3D array. And again, this is a nested for next loop for our rows, our columns, and the third dimension. So if we try running this application once more for the third dimension, we can see our 3D array has the letters as expected with 100 rows. We have wiped the array, taken the data out, redimensioned the array to have only 10 rows, and reloaded it from the file to show the original information is now back. If we have a quick look at the file, we can see there are our 3 dimensions, the 100 rows, the 5 columns, and the 2 in the third dimension. And the rest of the data is scattered through the file. So in summary, what we've achieved today is to create 2 generic functions. These functions allow you to load and save a string array to disk. Additionally, the functions place a header at the beginning of the file. This header specifies how many dimensions the array actually has, and the number of elements within each dimension. This gives you 2 common functions which are independent of the number of dimensions in the file. While there is a limit of 99,999 rows, this could be extended by increasing the size of our header. Additionally, the same approach could be taken for other types of array, but that might be the subject of another video. That's it for today. Thank you for watching.